Hello and welcome back to the Networking Fundamentals section of this course, where we're covering the foundations of Ethernet and IP. In this video, we'll be covering network topologies, the enterprise LAN and WAN design, that is the local area network and the wide area network. Now, network topologies are not explicitly mentioned in the exam topics. However, I do feel it's important to understand the common topologies so that you can have the vocabulary to be able to speak about this during your day-to-day work. First up, let's take a look at the spine and leaf topology. You may have heard of spine and leaf before. This is very common for data centers. This is a two-tier or two-layer topology. As we see on the right here, we have the spine up top and the leaves at the bottom, where the leaves would connect to servers or other end devices, and the spines up here are your aggregation between all of them. It's important to note that the spines are not directly connected, and that each leaf connects to all spines. This means that if you have server A here and server B here, if A wants to talk to B, it can do equal cost multipathing and go up all of these uplinks, because each one of them has an equal cost, hitting each one of our spines and then coming down to server B over here. If we need to add more bandwidth to our system here, we can simply go ahead and add another spine and interconnect all of our leaves to it. And then that will give us additional bandwidth due to the equal cost multipathing that can occur, which is where we split our traffic and load balance across multiple links which are of equal cost or equal distance from ourselves to our destination. The spine and leaf is very uncommon to find in anything outside of a data center. It's very excellent for what's called east-west traffic. Is if I have multiple servers down here, say a database server here and a web server down here, and these two need to communicate very often, this type of topology is very excellent for that type of business case because of the high east-west bandwidth here, meaning high bandwidth available between our end nodes. So let's take a look at a few WAN topologies here. First up will be our classic hub and spoke. A hub and spoke topology, as the name implies, has a hub device, some central core device, and multiple spokes. Here we have 3 spokes. The benefits of this are that we have full connectivity between all of our devices with as few links as we possibly can. We also have a cost savings in our WAN. Remember that these links here between our hub and our spoke, this is actually a WAN link. This might be several kilometers, several miles, or it could even just be a few hundred feet down the road. But likely, you as an enterprise or as a business don't directly own this link. You probably are leasing it from some service provider. You may have a campus fiber throughout your multiple buildings of your enterprise campus, and in which case you might actually own this link. However, oftentimes if you're connecting buildings in different areas of the city or through different states, things of that sort, then you will not actually own this fiber and rather will lease it from a service provider. Some of the drawbacks of this topology are that you're reliant upon a hub. All of your spokes, if spoke A wants to talk to spoke B, that traffic needs to come down through the hub and go up to spoke B. This not only gives us the opportunity for a bottleneck, but also potentially a single point of failure. If our hub somehow went down, even if this was a redundant set of devices and our redundant set of devices went down, all of our communication to all of our spokes and the spokes between each other is now cut off because the hub has now had a problem. And this might not even be a device issue that you run into. If you're leasing your WAN lines from a single provider, then although we have 3 links coming out here, all of those links might use the same utility pole outside your building. And if a car runs into that and brings down that utility pole, then all of your connectivity will be down. This not only is a lesson in perhaps having more redundant connectivity, but also ensuring that you have redundant providers that exit your building in different directions or by different means. Perhaps one uses the utility pole and the other continues underground. However, we'll talk about that more when we get to the redundancy section. So if we want to add a little more redundancy than our hub and spoke, we can go for the full mesh. Now, this provides our maximum redundancy. A full mesh is defined by every node having a link to every other node. So we have node A, B, C, and D. A is connected to B, D, C, B is connected to A, C, D, etc. Every node is connected to every other node. So any one of these could go down and we would still have full connectivity to every other node. In fact, multiple links could go down and we would still have connectivity, perhaps through another node, to get to every other node. The problems that you might run into this are potentially infeasible management. Sure, when we're looking at 4 nodes here, this isn't that many links. This is only 6 links, right? But if we're looking at 12 or 15 nodes or more, then we are looking at potentially an infeasible number of links that might also be very expensive. This has the most number of links, being a full mesh. And it's possible that you just might not be able to do this, at least not from a physical perspective. You may be able to establish full mesh connectivity from a more logical standpoint, perhaps through an SD-WAN solution, but perhaps not through a physical connection method here. But it is important to know what a full mesh topology is. So let's say you want to have more redundancy than just your hub and spoke, and you don't want to have quite the management headache or cost associated with a full mesh, then we can look at our partial mesh. A partial mesh has more links than a hub and spoke. It has more redundancy than a hub and spoke, but it has fewer than a full mesh. Given our 4-node example here, we have our 3 links from our hub and spoke, and let's say we've got node A, B, C, and D. And C and D we found are talking very often, so we decided to put a link between them so that they don't have to go through the hub. That is often what this ends up becoming, is that you start with a hub and spoke for just your basic level of connectivity between all of your spokes and your hub, and you find that 2 of your spokes need to talk very often, and you don't want to have the bottleneck of coming through your hub site here. So you decide to create a direct link between your 2 spokes so that you can offload that traffic from having to go through the hub. The having fewer links benefit here is also directly influencing our cost. So this cost less than a full mesh. Management, however, can get a little tricky if you're not well documented or doing this in a very logical, methodical manner. And some sites in a partial mesh will generally not have redundant connectivity. For example, node B here has a single link down to the hub. It does not have any redundant connectivity there. A lot of times this is acceptable. You might have a particularly low value site that's just some branch office, only a few workers are there. It's just not worth the expense to have that redundant connectivity. Or perhaps your site is just not that reliant upon the network. They do a lot of printing or other such things there and don't need to transfer many files or have reliable connectivity back to the hub. So that's our WAN topologies, our wide area network topologies. Let's now take a look at some example topologies for our local area network. First up, and you may have heard of this before, is the collapsed core, our two-tier LAN topology. This is very typical of a small or medium business. Now, there's not a set size of your company as to when you need to graduate to this type of formalized two-tier architecture, or when you even need to scale beyond that. This is usually what a small business network aspires to become. Generally, when your small business starts out, you might have a firewall, and then that's connected to a switch, and that connects to all of your servers and workstations, right? And then at a certain point, when you have a lot of workstations, you might be adding another switch. And then you might add some more workstations here. Maybe you have voice over IP telephones now, right? And you start going here and you add in another switch to handle your telephones. At a certain point, when you add enough devices or enough switches, you'll find that having either a single or redundant core switch will be very beneficial. You'll define this as being the one that all of your access switches connect to. And if done right, you will end up with essentially this design, where you have a redundant pair of core switches up in the top, and then you have all of your access switches handling your individual floors or individual office areas down at the bottom here. This is really excellent topology, very scalable. It's very resilient too. You can get pretty big with just having this two-tier design. Now, what happens though when your company gets to a certain point that when you add additional buildings, usually what you'll do is add another core or distribution layer. Say it's these two switches here, right? And that they will be fully interconnected to these. And then if you add another building over here, right? Then these guys will need to be fully interconnected as well. At a certain point, you could see with 2 or 3 more buildings, you might run into a problem where having all of these links here interconnecting our core or distribution layer is going to become a little infeasible and a little unmanageable. This is where step in our 3-tier traditional design, where we have a dedicated core layer that interconnects all of our distribution blocks. This is the ultimate in scalability. Generally, this would only come up when you start having many buildings in your campus, and you have some central building is the core data center, and you have a core switch or core set of switches to interconnect all of your distribution blocks. To take a look at what that kind of connection looks like is we'll see this diagram here. where we have our dedicated core and then our distribution blocks with all of our access switches at the bottom. Now, if you need to add additional connectivity or an additional building, all you need to do is take this distribution access block and copy it over here and go ahead and interconnect it. And there you go. You've just added another building onto your enterprise campus, and it is a very resilient, very scalable kind of topology. This is usually what you would find in a very large business. This is really just overkill for anything that is less than perhaps about 50 switches or so, because at that point you could just use a two-tier design and not have to worry about having dedicated core switches. Great. I appreciate you going through this with me. I hope that this has been informative for you, and I would like to thank you for viewing.